Every HTTPS connection begins with a negotiation called the TLS handshake, and the crown jewel of that negotiation is the cipher suite, a single named recipe that decides how two computers will exchange keys, prove identity, encrypt data, and protect integrity. Picture the client knocking on a locked door while the server peeks through. The client offers a list of ciphers it understands. The server picks one, slides its certificate under the door, and only then does the handshake complete. That picked name, like ECDHE, RSA, AES-256, GCM, SHA-384, is the cipher suite, and every dash separates a different cryptographic job. The first segment, ECDHE, is the key exchange, ephemeral Diffie-Hellman over elliptic curves. Both sides contribute fresh randomness to compute a brand new shared secret every single session. And because that secret is never reused, compromising today's key cannot decrypt yesterday's traffic. That property is called forward secrecy. The second segment, RSA, is the authentication algorithm. The server proves who it is by signing the handshake with a private key, and anyone holding the matching public RSA certificate can verify that signature. This step answers the question, am I really talking to the server I think I am? The third segment, AES-256 GCM, is the bulk encryption cipher, 256-bit AES running in Galois/counter mode. Once the shared secret is established, this cipher encrypts every byte of application data flying across the connection, turning your requests and responses into unreadable ciphertext. The fourth segment, SHA-384, names the hash used for the MAC and the TLS pseudo-random function in TLS 1.2. It verifies that nothing was altered in transit and helps derive session keys. Worth noting, in TLS 1.3, AAD ciphers like GCM bake the MAC directly into the encryption, so the hash name drops out of the suite. The cipher string gets shorter. The order is not arbitrary. It maps to the handshake itself. Key exchange first to establish a shared secret. Authentication second to prove identity. Bulk cipher third to protect the data. And the MAC last to guarantee integrity. Skip or scramble a step, and the whole protocol falls apart. Think of each segment as a tunable knob. Swap AES-128 for AES-256, and you trade speed for strength. Swap ECDHE for plain RSA, and you lose forward secrecy. Swap SHA-256 for SHA-384, and you change the integrity guarantees. Every piece is a lever, and the cipher suite name is the exact recipe you have configured for that connection. TLS 1.2 cipher names pack 4 jobs into one hyphenated string. Take ECDHE, RSA, AES-256, GCM, SHA-384. That tells you the key exchange is ephemeral elliptic curve Diffie-Hellman. The authentication is RSA, the bulk cipher is 256-bit AES in GCM mode, and the MAC is SHA-384. TLS 1.3 strips cipher names down to the essentials. The name TLS_AS_256_GCM_SHA-384 only encodes the symmetric cipher and the hash. Key exchange and authentication are fixed and signaled through separate extensions, not baked into the label. OpenSSL groups hundreds of ciphers into named buckets, so you can refer to dozens at once. HI collects strong ciphers with 128-bit or better symmetric keys. AES pulls in the AES family. ECDHE captures ephemeral elliptic curve key exchange. And aNULL flags anonymous unauthenticated suites, the ones you want to ban. The filter syntax is built from 4 operators. A plus adds a cipher to the list, a minus removes it, a colon separates groups, and an exclamation mark permanently deletes a group so nothing later can bring it back. Read HI. aNULL out loud. Start with everything in the HI bucket, then permanently strip anonymous ciphers. The colon moves you from one step to the next, and the bang means no later rule can resurrect that group. Default is OpenSSL's curated starter list, a sensible baseline that the project maintains, but not a guarantee of security. Treat it as a starting point you refine, not an ending point you trust blindly. Anonymous ciphers encrypt your traffic but authenticate nobody. Anyone in the middle can intercept the connection without either side noticing. That's why aNULL must always be disabled in production. A hardened filter looks like ECDHE plus ASGCM. aNULL. MD5. 3DES. You require ephemeral key exchange and modern AAD ciphers, then permanently kill anonymous suites, MD5 and triple DES, leaving only authenticated, forward secret, modern cryptography. In this demo we'll walk through 5 OpenSSL commands that let you inspect and filter the list of available TLS cipher suites. Each scene shows the exact command and its realistic output, so you can follow along on your own Linux terminal. We start with clear, a simple housekeeping command that wipes the terminal scrollback, so each upcoming result stands on its own. It's not required, but it keeps the session clean when you're documenting commands one at a time. Next, OpenSSL version prints the OpenSSL library version installed on the system. This matters because cipher availability, defaults, and deprecations all change between OpenSSL releases. Now the core command. OpenSSL ciphers v dumps every cipher suite your OpenSSL build supports, in verbose form. Each line shows the protocol, the OpenSSL cipher name, the aNULL/RFC name, the key exchange and authentication algorithms, the bulk cipher, the MAC, and the key length. OpenSSL supports a filter language that lets you include or exclude suites by algorithm. The simplest form is a positive keyword. OpenSSL ciphers v ECDHE keeps only suites whose name contains ECDHE, meaning elliptic curve Diffie-Hellman key exchange. You can also narrow by bulk cipher. OpenSSL ciphers v AES-256 lists only suites that use 256-bit ES in some form, ignoring weaker 128-bit suites and CHA-20 variants. Combining keywords like ECDHE plus AES-256 lets you drop weak key exchanges and weak symmetric ciphers in one pass.